So here we are with another question on diode connected circuits. So we have this circuit here and we are provided with the information. The diodes connected D1 and D2, they have built-in potential of 0.6 volt. Yes, it's slightly different, but normally we come across built-in potentials of 0.7 volt or 0.3 volt for silicon and germanium respectively, but sometimes you can get data like this, so don't get confused. You just have to consider the value whatever which is given in the question. Okay, so here it is given that the built-in potential is 0.6 volt, forward resistance is 35 ohm for these diodes D1 and D2. We have to find out this output voltage when V1 and V2 is equal to 5 volt, that is the first case. In the second case, V1 and V2 is equal to 0 volt. So for these two cases, we have to find out V out. Okay, so the first case. Now, when V1 and V2 is equal to 5 volt, pay attention that this end, this terminal, it is connected to 5 volt also. So what we have here is that both ends of the diode, they are connected to 5 volt. Okay, now I have already told you how a diode gets forward biased and reverse biased. See, both the diodes are connected to the same potential. Here, if the diode would have been ideal, okay, if the diode would have been ideal, that is, the potential barrier voltage would have been 0 volt, then in that case, this diode would have been activated, would have been on. For this ideal diode, no built-in potential, 0 volt built-in potential. But here we have been given that the built-in potential is 0.6 volt. So if we apply KVL in this closed loop, then in that case VD, the voltage across the diode, would be 0 volt, which is obviously lesser than the built-in potential of 0.6 volt. So it will never be enough to forward bias the diode. So in this case, when V1 and V2 is equal to 5 volt, that is, the P end is connected to 5 volt, the N end of the diode is also connected to 5 volt, both the ends are connected to the same potential. For this non-ideal diode with a built-in potential of 0.6 volt, it would not be enough to turn the diode on. So it will be off. The diode will be off. It will be open circuited. So what it means that both the diodes D1 and D2, they will be open circuited. Both the diodes will be open circuited. Now as they are open circuited, in this case here there will be actually no current flowing through these circuits, and here the current flowing through the 4.7 kilo ohm resistor will also be 0 ampere. It will be 0 ampere. No current flowing through this 4.7 kilo ohm resistor. So here the output will be simply, will apply KVL from 5 volt to V out. So just pay attention to this. In this case, here it is 5 volt, 4.7 kilo ohm, this is 5 volt, 0 ampere, this is V out. So if we apply KVL in this way, it will be 5 minus 0 ampere into 4.7 kilo ohm minus V out is equal to 0. This is 0, so V out is equal to 5 volt. So for the first case, output voltage is 5 volt. Okay, this. Now the second case, where V1 and V2, they are connected to 0 volt. So we can redraw the circuit as something like this. Again, this is 5 volt, .7 kilo ohm. Then we have the diode, then we have 270 ohm, again the diode, and 270 ohm, and both V1 and V2 is 0 volt, means we can consider them connected to ground. Okay, this is D1, this is D2. So here if you see the P end, this is V out. Now here if you see the P ends of the diode D1 and D2, they are connected to a higher positive potential. Okay, always pay attention to this, a higher positive potential, and the N end is connected to 0 volt. So in this case both D1 and D2 will be on. So on means we'll replace them with their equivalent circuit. Okay, so what is the equivalent circuit? It means we'll replace them with their built-in potential and forward resistance. Okay, first let us further cut it so that there is some space. We'll replace them with their built-in potentials and their forward resistance. The forward resistance value is 35 ohm, built-in potential is 0.6 volt. So 0.6 volt and forward resistance of 35 ohm. Then again the same here, 35 ohm forward resistance and built-in potential of 0.6 volt. This. Okay, we have simply replaced the diodes D1 and D2 with their equivalent circuit when they are on. Built-in potential of 0.6 volt, forward resistance of 35 ohm. Now if you see both these branches, they have identical circuit conditions. All the parameters, they are the same, 0.6 volt, 35 ohm forward resistance, 270 ohm resistor connected. Here also the same. So if current flowing from this 5 volt source is I, then the current through each of these branches will get divided equally. So if it is I, let's use a different ink, okay, so that there is clarity. Okay, if this is I from the source, then the current flowing through each of these branches will get divided equally. So it will be I by 2, here I by 2. Okay, this. Now here if we now put KVL here, okay, if we put KVL here in any of these paths, let's say we put KVL from here, okay, it is 5 volt, see, please follow the path which I am taking, like this. if we apply KVL in this direction from source to ground, this is ground, this is source. If we apply KVL in this direction, the KVL equation will be 5 minus I into 4.7 kilo ohm means 4700. I am converting into ohms because the remaining resistances, they are in ohms. Then minus 0.6, which is this, then minus I by 2 into 270 plus 35, 270 ohm plus 35 ohm. This is the KVL equation. Okay, then that implies if we bring all the I on one side, the current parts on one side and voltage, the remaining parts on the other side, that is 5 minus 0.6 is equal to I into 4700 plus 1 by 2 into 270 plus 35, which is how much? 305. Yes, 305. This. Okay, that implies I will be equal to 5 minus 0.6 divided by 4700 plus 152.5, which is equal to, let us calculate, 5 minus 0.6 divided by 4700 plus 152.5. So it is coming around 9.067 into 10 to the power minus 4 ampere. Okay, 9.067 into 10 to the power minus 4 ampere. This is the current I here. See, this current I. Our objective is to find V out. Our objective is to find V out. So let us focus on this part only. So we have 5 volt here. We have 4.7 kilo ohm here. We have the value of I, which is equal to 9.067 into 10 to the power minus 4 ampere, and we have to find out V out. So if we apply KVL here, from here to V out, from this point to this point, if we apply KVL in this direction, then we'll have 5 minus I into 4.7 minus V out is equal to 0. That implies V out is equal to 5 minus 4.7 I, which is equal to 5 minus 4.7 into 4.7 kilo ohm into I, which is 9.067 into 10 to the power minus 4, which will be equal to, let us calculate, which is coming around 0.738 volt. Okay, the result is 0.738 volt, that is V out. So the V out value is equal to 0.738 volt. Okay, so see, what are the concepts here that we wanted to understand? First concept, from this first part of the question, where both the ends of the diode were connected to the same potential, for the conditions that were specified in the question, the diode is not an ideal one. Okay, is not an ideal one. So that's why For the non-ideal diode with a built-in potential of 0.6 volt, both the ends of the diode being connected to the same potential will not be enough to drive it to the forward bias condition. So it will be off, no current will be flowing through the 4.7 kilo ohm resistance, no drop. So the entire supply voltage will appear at the output. Vout is equal to 5 volt. That's the first case. In the second case, both the first P end of the diodes, they were connected to 5 volt, and the N ends were connected to ground, 0 volt. In that case, it will be sufficient to turn them on, to drive them to forward bias mode. And since both these branches, they have identical conditions, the same current will flow through it. It will get divided, the source current will be get divided equally. So we just applied KVL from source to ground to find out the value of I. Then after finding the value of I, we applied again KVL from this source node to output node to determine Vout, and we got the output value as 0.738 volt. Okay, so this is the solution here.